Okay, well, welcome. Thanks everyone for joining. Maybe good morning or maybe a good evening, depending where you're at, or good afternoon. Yeah, really appreciate you joining. We're gonna go through as the title says, the second open discussion for the ICON-ModEx research effort. And want to thank my co-authors that are listed there and funding that's acknowledged there as well. And I want to start with a couple challenges that we're trying to do today. From a kind of a technical science side, the scientific focus is about respiration rate in riverbed sediments, which is a really important aspect of river corridor function. But at the moment, we really can't predict respiration across systems, across river corridors. The more of the engagement challenge, to move beyond kind of just the technical, is a key goal, a key challenge here with this effort is finding ways with you all to make changes to this effort to maximize the benefit that it can have across a broad range of stakeholders. Everyone on the call here I would consider a stakeholder of one flavor or another. We use that term as inclusively and as broadly as possible. And so to do that, we really need your feedback and your help to try to find ways to maximize benefit. And then kind of zooming in a bit more, today's topics, they are similar. If you join the first of the first call, we're going to go over some similar material, though I'd encourage you to stay tuned in because there are some changes. And we have made modifications to what we are doing from a technical side based off of feedback, and we'll talk through that. And we want to get some feedback on our methods as well during today. There's a link there, and I believe, I can't quite see the chat, but I believe Amy's probably put in a link to this slide deck. So all the links are live. I'd encourage you to go. It's just a Google slide deck. That's a summary of this project. It's a couple pages if you'd like to dive in and learn a little bit more. Okay, so I want to start then thinking about sort of the value of this. Why would you, thank you for being here. And, if you're thinking, do I want to engage in this? I'm not quite sure. I want to encourage you to stick around and to think about how this can be valuable to you. And on the screen here, we have some of our thoughts of this is the way that we might think people may gain value from engaging in this effort. And that can take many different forms. You may be a river corridor scientist and like super interested in the technical stuff, or you may be someone that is interested in helping to shape how this kind of science is done. Okay, better, thanks. So here's some examples. By engaging in this effort, you can help shape how it actually functions and how we collaborate, how we do this openly with you and other stakeholders. Shape the process. You can help think about and guide how we can use this effort and the outcomes of this effort, the data, the protocols, the engagement approaches. How can we use those to enhance educational opportunities? If you're an educator, there may be opportunities for you to kind of lean into that and help us design ways for your students or other people's students to gain value from this. If you're like really into river corridors, you might want to engage with this to help design and develop the technical aspects to drive towards transferable knowledge and models. And to zoom in even further on the technical side, if you're working and doing science in a river system, you can generate data for free from your system by helping take samples. And then you can use those data, as can other people, to develop publications or proposals or whatever kinds of scientific outputs are of interest to you. And so those are kind of from our view. If you see other values to you, other ways we can change this to bring other kinds of values, please let us know. There's going to be a link to a feedback form at the end of the slide deck, which you should have access to now. Okay, and I will say throughout this, feel free to use the raise hand function. I can see, I should be able to see that, or Amy can interrupt and let me know if there's a question. Please just ask it as we go, as you like. Okay, so on the first slide, use this acronym of ICON. Well, what is that? You may have heard this before. As I mentioned, I'd encourage you to stay tuned in if you've heard it before. We have found that it takes a few times of hearing this for it to like kind of really sink in a little bit deeper. And so, it might help to kind of go through this again with us. And what ICON is really, it's a set of values to guide intentional design, really of any project, of any scale. Could be a big crowdsourced thing, could be an individual group doing a project in a specific location, could be modeling, could be lab activity or a field activity. It's really values that people can use for intentional design. And the letters are for I, for integrated, is purposefully finding ways to couple different kinds of disciplines together: physical, chemical, biological, social attributes. How can we bring those together more directly and explicitly? The C is for coordinated, in the sense of generating data using consistent protocols across systems, across research groups, so that we can actually generate data that is interoperable with each other and across time, space, and efforts. The O is for open, and that is not just publishing your data at the end or making your data or your paper open access. That's certainly important, but being open throughout the entire research lifecycle, which can mean many different things to different people in different contexts. And of course, publishing metadata and data using FAIR principles. And the last letter is networked, or N for networked, where research is designed with a broad range of stakeholders to maximize and ensure mutual benefit. This is what we're doing right here, and thank you again for engaging with it. And this is all four of them together make ICON. And one thing I want to emphasize is we have found that often when we present these ideas, these values, these principles, people's minds often gravitate to the open. And people think, okay, yes, we're doing open science, which yes, we are, but we're doing more than that. This is a set of principles that go beyond open science. And I'd encourage you to think about that and kind of think about how these might be useful to you beyond this particular effort. And we'd be happy to engage with you if these are of interest, if you want to learn more, in particular through the ICON Science Cooperative, which is linked there at the bottom. Okay, so that's a brief intro to ICON. Another acronym that I used at the title slide was ModEx. And ModEx is the idea of model experiment iteration for mutual learning. And really, in a sense, the idea is very simple. It's really the scientific method. It turns out it's pretty hard to do this particular kind of the scientific method. But really going from observations where we're generating conceptualizations, mechanistic understanding, and parameter values, and feeding those in to models of different kinds. Those can be mechanistic models, those can be data-driven models, those can be hybrid models, and then using those models to learn and also then to guide additional data generation. And it's this sort of forever loop, and I've also seen it presented kind of as a spiral where the knowledge system is changing through time. So it's not really flat, it's actually moving through time. And so we're putting those two things together. There's ICON that I was describing, and there's ModEx. And the ICON-ModEx effort is integrating those two together. In particular, where in our particular case here, we're using an ICON approach to help us understand how to best generate observational data from field samples and feed those in to the observational piece of the ModEx loop. And with the modeling side, I'm going to give you a bunch of details about that. And so ICON can enhance the power of observations within this ModEx loop. And again, doing that with you all to maximize the mutual benefit of doing that, of generating those data. Okay, so our science focus is using this ICON-ModEx approach to understand and help predict sediment respiration at the moment across the contiguous US. Though if you're not from the US and you're interested in international sites beyond the US, I encourage you to stick around. I'm going to speak to that a little bit later. There are some opportunities to go beyond the US as well. But for the moment, the way this project is funded, science is focused on the US in the moment. Okay, so we're looking at artificial intelligence-based predictions of sediment respiration. That's a map from Stefan that's on the left there. And one aspect that we got feedback on after the first call of this series was that we really needed to be a little bit more specific about our research goals and help those specifics guide us to the details of how we're actually implementing this. And so it says there on the slide, we edited these per feedback. So thank you for the folks that gave us that feedback. And here's some examples of what we're focused on from a science perspective and kind of research goal perspective. One of those is can we use this ICON-ModEx approach to continually improve AI-based model predictions of sediment respiration? We've certainly never tried to do something quite like this. Maybe others have. If you have, would love to get your feedback on it. But can we use this to actually turn that ModEx crank in a really useful and large way with the community to improve AI models in a continuous way? Then going down, as we do that, we have some initial estimates of how the relative importance of different variables for influencing sediment respiration across the contiguous US. But as we do this, as we crank this ModEx loop, does the relative importance of different variables, does that change, or is it stable? That's very important to know as we think about sort of mechanistic understanding and interpretations. Going down further, are omics data really necessary to achieve a high skill AI model for sediment respiration? Or can we use data from, say, satellites, or not really basic, but sort of more spatially contiguous kinds of data that we can often get from public repositories? Or do we actually need really detailed microbial data, organic matter chemistry data, metabolomics? Do we have to have those to actually build a good AI model? Even if the AI model isn't mechanistic, that's giving us a signal or information about what the governing processes really are at this large scale. So that's a question for us. And then sort of, this is all kind of looking down into the sediments themselves. We're also looking back up and trying to take this the AI model into a large scale mechanistic model to ask the question of how do basin scale fluxes of carbon and nitrogen respond when we incorporate AI predictions of variation in sediment respiration. That is, how important really is this variability in sediment respiration? We think it's probably pretty important, but that's a mechanism or an approach to actually quantify how important it is at the basin scale. So those are some of our research goals. Hope would be interested, we're certainly interested in discussing those as we go. And I'm looking for hands, but I'm not seeing any hands right now, so I'll assume everyone's on the same page or following along. Again, if there's questions, please just raise the hand and ask away, or just unmute if that's easier. So let's start to keep zooming down here. In terms of implementing ICON-ModEx, what does this actually look like? So this is a high-level overview of that, where we're starting from WHONDRS data, and we're not going to present WHONDRS in this slide deck, but basically WHONDRS is a research consortium that many of you have participated in to crowdsource samples to generate data in river corridors. So we're using those data. Those data have been fed in to a suite of artificial intelligence models via a Parallel Works, which is a small business that we're collaborating with in this effort. They've also ingested data from public databases to build the suite of AI models to predict respiration. That's the map down here across the contiguous US. And then we're using those those model predictions to then guide additional crowdsourced samples via WHONDRS, which is what we're really driving into here. As I mentioned, we're also then using that AI model as we improve it to predict variation in sediment respiration, specifically within a basin in the northwest part of the United States. I don't know what people can mute. So using that, I'm really getting bad feedback. I don't know where this comes from. Okay, yes. Nope, not better. Anyways, I got to keep going. So, okay, so that's going to be put in this mechanistic model, northwest part of the US, basin scale, again, to look at the influences of variation in respiration on basin scale carbon and nitrogen fluxes. That's not really pictured here, it's lower right hand. So how does this, let's just keep going, like a little bit more detail. How does this really work in kind of a stepwise process? And as the title says here, and I've said this multiple times, I'm just going to keep emphasizing this, that we want to try to do our best to meet the needs of you all. How can we make this useful to you? And so this is our process. And again, if you would like to engage with us to maybe modify this process, That's a great way to engage and help shape the way this whole thing works. The way it works right now is initially we come up with some science questions, some science drivers, and that's like the core project team is coming up with those. And then we come up with an initial design. That's number 2 there, just a preliminary design. This is how we think we would answer these questions. And then we engage in what we're doing right now. We're getting community feedback across hopefully a broad range of stakeholders, and to find ways to make changes to meet needs and make this useful to folks. And from there, we kind of zoom in, we really refine the details, we build sampling kits, and then we ship those out to folks that would like to volunteer to collect samples and help crowdsource these samples. And those kits then come back to us and we pay for the shipping both ways. We have standardized protocols. We generate the data. We work with user facilities to do this in part, and other resources as well. The Environmental Molecular Sciences Lab, or EMSL, is one of them. The Joint Genome Institute, or JGI, is another. And then we generate data. We, of course, we quality assure. We do the QA/QC, and we publish that on an archive called ESS Dive. That is the Department of Energy's Environmental System Science data archive. And we publish FAIR data there openly. And you'll notice the sequence. That comes before we're publishing manuscripts. So we try to do that where we get the data out first, manuscript second. And increasingly, we're also working to crowdsource not just the data and the samples and the approach, but also the analyses and the writing to engage with whoever's interested across the whole research life cycle. So that's how it's working right now. And as I said, we're really at stage 3 right now. And after this call, we'll pretty rapidly move on into the stage 4 and 5. Okay. And then let's keep going in a little bit more detail. So I mentioned in the previous figure that we're starting with WHONDRS data that was previously crowdsourced. So this was done in a 2019 campaign. And you can see that the locations there are all the circles. There's, most of them are in the contiguous US. There are, a handful or more that are international. And what this did is it provided pretty diverse data to enable this artificial intelligence modeling. And we generated pretty diverse data. And for us, there was lots of places. There's about 100 locations globally. And on the left, I'm not going to go through all those data types. It's not meant to be beautiful over there, but it's basically giving you a sense of the kind of data that were generated from this initial effort. And there's actually some more data types than that, but that just kind of gives you a sense. And that relates to one of the questions that we asked on the first call in this series.
Audio turned on?
Getting feedback again. One of the questions that we asked was, should we, in this ICON-ModEx effort, should we generate just a small number of variables in lots of places, or deep information in a few places? And it was very useful feedback to hear. There was really split opinions, honestly, of the folks that were participating. And we're going to get some more feedback on this today. And one thing we wanted to emphasize is that we started with pretty deep data across lots of places to begin with. And I want to just mention that to put that in people's thinking as you're thinking about, does it make sense to pursue this new ICON-ModEx effort with a, kind of a thin layer of data in lots of places, or deep data in a few places? Okay, so that's sort of where how we generated the data to begin with. And then, in particular, Stefan Gary, who's on, has been doing a bunch of AI modeling with those data, those WHONDRS crowdsourced data, but then combining them with public databases, for example, the GlowRich database. And so I want to walk through this figure here. We have our 2 axes. We have observed oxygen consumption and predicted oxygen consumption. And we're using those, and what those are they're lab-based measurements of O2 consumption, using that as a proxy of respiration rate. And so if you go back to the previous slide and think about what we were doing, people were sending sediments to us. They're all coming to Pacific Northwest National Lab in Washington State. Sediments are coming to us. We take those sediments, homogenize, sieve, and then put into a vial, add water, native water from the system, the stream that was sampled, and then measure oxygen consumption over 6 hours in this case. So that was our observation. As I said, a proxy of respiration rate. And then we have all the other data types. And Stefan put all that together and ran a large number of different AI models to try to build a predictive AI-based modeling set to predict O2 consumption. And so that's the image on the right. And to help, there's lots of circles and lines and things, and just kind of walk through it. The training set and the test set are the solid and open black circles, the larger circles. The 1-to-1 is the black line. And one thing I want to emphasize is that respiration rate is increasing as you go to the left or go down. So it's the more negative the number, the faster the consumption rate. So respiration is increasing to the lower left. The small circles are different realizations of different AI models or approaches, and the short little acronyms of those models are listed in the legend that's embedded in the panel there. And one thing I want to emphasize is that then, okay, well, multiple things. So you have then the red lines are the correlations from the test set and the training set. And one thing you can see is that there's this really pretty strong bias as you go towards higher respiration rates. The model performs poorly, and you get this really strong bias where it's really under predicting. So the observed rates are, I'm sorry, the other way around. The observed rates are much lower than the model is predicting. Hopefully I got that directionality right. But there's a strong bias, and it's pretty systematic there. And this is also related to a question we asked folks last time. How should we use this model performance or poor performance in some ways to guide us into where we should be sampling next? And, oh, I do see a hand up. I think Ricardo.
James, this is interesting data. I was just wondering about if you have had any opportunities to, at the same site, quantify the differences in respiration over different seasons, and how, if there is a huge change, for example, how can that be interpreted within the sampling across the United States? For example, one side in the summer in one place could be similar to another side, in the other coast in a totally different season. Any ideas on that or data?
Yeah, a couple thoughts on that. So, okay, first of all, the sampling design was such that we got 3 different sediment samples from a single stream reach. So these were 3 different depositional zones within, roughly 100, 200 meter kind of spatial scale. And so we're treating those independently. They're 3 different measurements. They're incorporated independently in the modeling. And so the broad scale metadata, if you will, it should be the same across all of those. And this then starts to relate to a key question that I listed on previous slide. Can we use these broad scale data, spatially contiguous data? Is that all that we need to build an AI model that has good predictive ability? Or is it necessary to have more detailed data? I was presenting this as like omics data, microbial data, or metabolomics, or organic matter chemistry more broadly. Or maybe there's some other kind of data that's really needed that varies temporally, more dynamically. So you can imagine that the chemistry will be changing dynamically through seasons, as you were noting, spatially, within a given system. And if those kinds of very dynamic elements or aspects of the system are really governing the variability in respiration, then I think what we'll learn is that we may not be able to simply use spatially contiguous GIS layers of somewhat static variables. We may truly need to measure very dynamic molecular properties of the system to be able to build a good AI model. And so those are my current thoughts. Stefan, I don't know if you had other thoughts about that. I mean, you were the one handling the data and developing the models.
Oh, hi. My only other thought was one of that these respiration rate measurements were happening in the lab. So they're not in situ, but in vitro, in the sense that the temperatures at which they're incubated at are going to be different from what they're actually in what they were in the river water. So that's another important distinction to make when thinking about, say, seasonality, say temperature impact on respiration rate.
Yes, thank you. And one other thing I'll say, and I do see a couple hands. One design element that we've been working through and that was suggested at the last community discussion, open discussion, was the idea of doing some time series sampling in a couple sites. And so we are trying to build that into the design to try to get a handle on how temporally variable the respiration rates are at a given site. And you can imagine immediately that there's a big challenge there because it's kind of impossible to go and sample the exact same place in a river across from like spring to fall because the river's going up and down. So would love to get some feedback on that of how we can do that best without being like up in the riparian soils in the spring and then down in the middle of the channel in the fall, just as the rivers go up and down. Let's see, I'm seeing two hands. BK, looks like you want to jump in.
Mm-hmm. Thank you, James. This is really interesting data with this AI modeling. It's a kind of following the heterogeneity questions. So seasonality is one thing, but also other aspects about the way measure the oxygen consumption. So again, the sample was taken out all homogenized, integrate the different depth. But when you look at to the oxic layer where all the respiration is a very thin interface between water and the sediment interface. So it could be the difference between modeling versus actual measurement coming out, maybe where the actually real activity is occurring, where the more thin layer instead of much deeper integrated all the sediment depth we collected over time.
Yeah, and that's a really big challenge here with this kind of a study. And if people have ideas on how to solve it, would love to hear them. So one thing to emphasize is that in the sampling protocol, we're following the U.S. National Ecological Observatory Network, or NEON. We follow their protocol of sampling surficial sediments, so 1 to 3 centimeters, which I realize in some systems will be anaerobic in even that shallow of a depth. We do our best, considering the very broad range of systems that this kind of an effort samples from, do our best to try to standardize that, at least to try to stay pretty shallow. And then, yes, as you say, it's all homogenized. So any kind of depth variability in that scale is just wiped out. And then we're adding, oxygenated water and shaking and mixing as we're measuring oxygen consumption. And so we try to replicate a system in which there is at least a pulse of oxygenated water moving through, maybe during a flood event or something like that, or the sediments are being, turned over. But it is a lab measurement. It's contrived, it's artificial, and there's always trade-offs with measuring things in the field, measuring things in the lab. As Stefan was saying, we're trying to at least have consistency in the temperature, the approach, as best we can, the starting oxygen, to make things as comparable as possible across systems. But when you do that, you lose some reality at the same time, just baked in trade-offs. So if you have thoughts, BK, or other people have thoughts about, how do we find our way through that challenge to generate information that's really valuable, would love to hear it.
Yeah, I was wondering whether you could actually getting the small intact core, putting into like some sort of the long, like ICON buyer like those, and then slice it in, and then send it to you guys, and then do like using the carefully adding the oxygenated water, and then using the either the oxygen probe or opto types of the sensor to measuring them.
Yeah, so I think there's some potential there, and we've been doing some optoed work that would certainly could be used in that kind of a setup. And I think one thing that comes to my mind is that will work in some systems, but not others. Like if you think about systems like a gravel bedded river, these fine sediments are in these little interstitial spaces, and it's like all these cobbles and boulders and stuff everywhere. And honestly, some people have told us they struggle to collect even like 100 milliliters of, finer grained sediments because they're having to go around and kind of pick it out of the interstitials. And so that could certainly work for the finer grained systems where you have a nice kind of depositional, fine grained, somewhat homogeneous location. And it is really tricky in riverbed sediments, and they're a little bit, well, I mean, some soils are like that too. We've struggled to get actual intact cores, but please, there's feedback form. Throw your thoughts in there. We're always trying to innovate and think and grow and change designs, and it may influence a future effort as well. That could be, focus on kind of intact cores. Be pretty cool. Thank you for that, BK. Hyun, looks like your hand's up.
Yeah, so I have a couple comments. One, you have shown the linear sequential steps to collect data to the benefit of entire community, and I think the role of AI is significant there. And then we can improve that workflow as a cyclic instead of a linear, because that AI suggestion for next data collection might be changing depending on the availability of the data. Data will keep increasing. Therefore, I understand that, but at that's end of that linear path, then we can make a cyclic path that how we can generate next round of data collection campaign. There's one suggestion. And then role of AI is significant because AI will let us know and then at what time and where we need to collect data, what type of data to improve predictions. But here that this figure shows that really some key variables or relationships are lacking enough to predict respiration rate. So probably my suggestion would be that we can think about formulating dimensionless numbers. In my past experience, I had a hard time to identify the universal calibration curve based on original variables. However, after defining appropriate dimensionless numbers and many data across different scales were able to be converged into single universal curve. AI may or may not help with that. Therefore, domain knowledge will be important. Domain scientists can help. What are appropriate dimensionless numbers that will facilitate, AI model development as well. So probably there's a room for collaboration between AI modelers and then domain scientists.
Thank you. That's a great suggestion. Dimensionless numbers are so powerful. I'm not a pro at them. I know, Hyun, you are a pro at that, and I really appreciate that feedback. Stefan, I don't know if you wanted to just a quick thought about that or.
My only thought, and this, I'm not an expert here, but Hyun, are you referring to like a respiration rate coefficient or like a reaction rate as opposed to the respiration rate, which would be oxygen per hour, basically?
Any ways we can non-dimensionalize respiration rate, for example, time kilo number, or there are many defined dimensionless number, but there are more complicated function of dimensionless number that combines many different already existing dimensionless numbers, but it's difficult for human to identify those complex functions. Therefore, domain scientists can generate all possible dimensionless numbers that are currently being used in the area, chemical engineering or ecological area, everything. And then AI may be able to identify how to combine those dimensionless numbers as a nonlinear functional form to improve or maximize the correlation between the predicted dimensionless number newly defined versus same dimensionless number measured. So that's an idea.
That sounds great. Thank you.
Thanks, Yun. And Amy, if you could, I sent a paper out recently to our River Corridor project about dimensionless numbers. Or Hyun, you may have it. Just maybe I sent it 2 days ago from a different group, looking at stream metabolism and some dimensionless number analysis. If someone has that link and can throw it in the chat, just for people to have some context, specifically around stream metabolism, that'd be appreciated. Okay, I'm going to keep rolling. Not seeing more hands. So how are we really guiding, how are we using AI in this particular effort? Well, I showed you this map before, and both of these are from Stefan. And so these are the predicted respiration rates. Again, the more negative the value, the faster the rate. And this is the model uncertainty. You know, you're seeing before on that last slide that the uncertainty increases as the rate increases. And so there's some real spatial clustering to the patterns of where the model is less or more uncertain. I want to use that to guide us. And so I also want to go through some feedback that we got on the last call. I'm sorry, there's tons of text here. I want to kind of step through the details here one by one. And we asked the participants a number of questions. Let's go through these one by one. We got feedback, and we've made some modifications based on that feedback. So the first one, as already alluding to, is should we measure lots of things in a few places or a few things in lots of places? There's this inherently baked in trade-off in doing that. And I do want to emphasize, again, that 2019 campaign, we tried to do lots of things in lots of places. That's really hard, and thank you for everyone that contributed to that. And we used a polling system. We're going to use that again today. But basically, the short story is the polls were pretty heavily in favor of doing a few things in lots of places, but there certainly was some strong opinions on the other side as well. But we have to make a choice. And so our current plan is to restrict the number of data types so that we can sample in more places. You know, thinking about how do we, turn this ModEx crank as best we can. That really requires lots of data, which means we have to sample in lots of places. So we are going to go that direction, though. We're going to ask for your feedback on that at the end here. I think we're doing okay on time. So types of data to generate. This is another question that we asked, in addition to sort of the standard metadata that we always gather, and sediment respiration. Like, we have to have sediment respiration to do this project. So based off of the feedback that we got, this is the selected suite of analyses. So people pretty strongly felt that we should be getting surface water, ion concentrations, and organic carbon concentration, which is NPOC. In addition to surface water, the respiration rate is made on the sediments. And so people thought, okay, yes, we should be getting sediment, bulk, carbon, and nitrogen. There's some pretty strong opinions and voices on that. Ion concentrations, we interpret that as water-soluble ion concentrations coming off the sediments. Doing mass spectrometry, specifically FTICR mass spectrometry to characterize the organic matter, grain size analysis, and microbiome data, specifically metagenomics and metatranscriptomics. And so those are the data types that we're zooming into to generate. In addition to, you're in the field, you can get a sense of, is this a braided system? What's the vegetation like? What's the weather like today? Lots of that kind of metadata coming along for the ride as well. And we'll again ask you to think carefully about these choices. We're going to ask you your opinions on these choices. Something else is there was significant interest in this effort providing subsamples to folks that are contributing and helping. Though no one told us the exact subsamples they wanted, and so the feedback form has some questions about that. If you're really interested in getting subsamples of some kind, please let us know. We'll work with you as best we can. We can't do everything, but we'll do our best to work with you. And so our plan is we're going to be building the sampling kits, refining the sampling protocol to enable those specific data types, and as I said, do our best to accommodate collaborator requests for subsamples. Another question had to do with the timing of sampling. Do we do a snapshot in time, like a really compressed in time, or do we just take samples on a rolling basis through time? Again, there's always different opinions, but the poll votes were pretty heavily in favor of this rolling collection, basically starting collections in the spring and having them roll in from different locations through time so that we can try to turn the ModEx crank. So we get 4 or 5 kits back, we get the sediment respiration measurements, and we feed that back in the model. Stefan does his thing, and we update the priority list of, okay, now they were seeing model uncertainties changing in this way or that way, and we can change where the next samples should come from. But also, I mentioned, so as I said, we're going to try to do that. We're going to do this rolling basis, as rapid ModEx as we can. But as I mentioned before, we're going to try for at least 4 to 5 time points at 1 to 2 sites. We can't do time series everywhere. That's just way too many samples. And so to get some sense of within site temporal variability, that's the current plan. Again, happy to hear feedback on that. How to guide site selection. This is another question we asked. Do we focus only on locations with high model uncertainty? The feedback was no. That was our initial thought. Feedback was no, don't do that. There was pretty strong voices that we should, or strong voice from the polls, that we should try to focus on expanding the environmental extent that is being sampled. And the second place in the polls was using model uncertainty. So what we decided to do, and again, we're going to get feedback on this, is we're combining environmental extent and model uncertainty together into a prioritized ranking. I'll show you what that looks like in the next couple slides. How to find collaborators. In short, people voted for basically everything, like keep communicating in all possible ways. I think one of the highest votes was more community calls like this. So we heard you, here we go. Thank you for being here. Another key thing was connecting with educational spaces. So classroom could be at any kind of level. And so what we're going to do is we're going to keep communicating as best we can using all platforms, email, social media, the listserv, the distribution lists, community calls. And then at the same time, we are actively working with our management and with DOE to solve some of our permitting restrictions that limit our ability to engage with educational spaces. I'm not going to dive into the details right now, but we are putting a pretty serious effort into that to expand the ability to engage with a much broader range of interested parties, in particular with respect to the sampling specifically. We can engage with anybody outside of the sampling, but the sampling is at the moment a little bit restricted. We're trying to get to overcome that limitation so we can actually listen to you and act on that suggestion of really engaging in educational spaces. So those are feedback and things we've been, as I said, we're trying to make decisions and hear you all and move forward. And I'm not seeing any hands, so.
We have some questions in the chat.
Okay. Let me see if I can have a look here. Oh boy, there's a whole bunch. So I'm just starting at the bottom. Let me see. So I think this has come from John Barger, that we've tried to keep our methods consistent through time and do testing, gives us confidence in comparisons. So if I'm sorry, I'm trying to read and think at the same time here, but yeah, we have tried to do as best we can of staying consistent for interoperability through time, through space, across these different campaigns. And that's cool, excellent. Neon has data on particle size, that's That's super useful. So Sammy's question about primarily agricultural or urban. So yeah, that's a super good question. And the initial data were, as I recall, primarily in quote unquote natural systems, but not exclusively. There was definitely samples coming from some ag areas, some urban areas, some coastal zones as well. And I don't remember, Stefan, are there data that are going into the AI model at the moment about land use of the upstream catchment?
Yeah, so there's a couple questions about sediment type in the chat, and so in the slides that are presented here, I needed to have a database that went across the continental United States, and so even though the WHONDRS data collect sediment information, the sediment type at each of the WHONDRS sites, in order to make a prediction, if I'm using sediment as an input variable for the prediction, I need to have sediment across the United States. And so the NEON database sounds absolutely awesome, and I look forward to including it and merging it with the rest of the data. In response to Tim's question about including the mean grain size, I did run an AI model that predicts respiration rate only at the WHONDRS sites just to get an idea for how well can we predict respiration rate within the data set by itself. And so yes, that model used sediment type and grain size, and those types were considered important by the model, but I wasn't able to do it for the slides that are presented here.
Okay, and can you speak to land use variables? Are those included at all?
Yes, so I used large-scale land use, effectively GIS layers from the River Atlas database, and so they had things like the percentage of forest or the percentage of cropland and that is distributed across the domain. So I could co-locate those data at the WHONDRS sites and then use those variables as inputs at predictions at sites where I did not have the respiration rate.
Excellent. And let's see, Eric, I saw your comment about ATP. Thank you. We should probably build that in. Okay, I hopefully capturing the majority of those questions. Sorry if I'm missing something. Someone shout out and tell me. Looking at the clock here to try to get through as well. So this is the event again. Stefan's doing this stuff. So combining model uncertainty, environmental extent. I'm not going to go through the details of how we did that, but these are the maps that come out. You'll notice this global map. So Stefan did this globally. And again, I do want to emphasize again that the current effort that we're talking about today is about the contiguous US. However, WHONDRS and our team are interested in global river corridors, and we do have some upcoming efforts that will be global. And so I encourage you to stay engaged with these kinds of efforts. And please reach out to us if you want to engage on a global scale. Let's see. So this is the map of basically priority. The hotter the color, the higher the priority. You can see it clusters spatially. And this is a map of the top, I believe, 100 sites, something like that anyways, across the, just the top 100. Here you go. This is how they fall out. And so one thing you can see is that they are distributed across the contiguous US. There's certainly some clusters, there's some singletons. And so the idea is, how do we start? Like, what's our next step? Well, let's start with 15 sites or 15 clusters. And I just put these on here, just red dots. There's nothing formal about that. But if we start with those 15, we're basically hitting these sort of 15 zones of high priority, if you will. There was also a suggestion in our last call that we also include a few points that have low uncertainty, sort of from a validation, like, okay, you say it's low uncertainty, is it? Like, does it, do you get pretty close? I like that idea as well. I didn't build that into this particular slide, That's something we haven't talked deeply about on the project side. But the idea is, let's start with these in early April this year. And this is the really short a protocol. So there's a link here to the full protocol, pretty detailed. We would love to get feedback on the detailed protocol. If anyone is willing to share your time and thoughts, please head to that link and dive in there, provide any thoughts that you have. In short, basically you go to a site based on the priority map, locate depositional zones, we'll focus on fine-grained sediments, deploy an oxygen sensor that's shown to be important in the model. We'll provide the oxygen sensor, metadata, photos, filter water. We use 0.2 micron always to get those aqueous data. We get some samples for ions as well. Filter some more water and use the filter for microbial data, unfiltered water for lab incubations, fine-grained sediments, superficial sediments, as we were talking before, into bottles. That's what's used for the lab incubations, the sediment respiration. Sediment goes into RNA later for sediment microbiology. All the samples go onto ice, 4 degrees Celsius, not frozen. They ship the next day to PNNL. So sorry, that's so brief, we're kind of running out of time. If people have thoughts on any of that, would love your feedback again. Please reach out to us with those thoughts. I also want to emphasize, I mentioned before subsamples that seem to be of interest to people, and certainly some folks on the call have previously received subsamples and provided data back to WHONDRS using their own resources. And thank you very much for doing that. Ado, I think, is on the call potentially. His group recently did that for flow cytometry data. So this is an example where we're doing that with a project we have here. This is my early career project where I'm not going to go through the details. Short story is we're using some of the sediments that are coming from this effort to do an experiment in the lab, like a wet-dry experiment tied to respiration rate, organic matter chemistry, microbiology. And so we don't have time to go through the details, but we are doing that ourselves, and we would like to offer that up to people. And so please reach out to us if you have interest in getting some samples of some flavor from this effort. So your feedback, super critical. We've already had some discussion. Great. Would love to hear more. The recording of this and the previous call are on the WHONDRS YouTube channel. This is the email to reach out directly. There's a feedback form here. It's a Google form. There's the protocol link. And then the last thing we want to do is hit these polls if we can cruise through them pretty quickly. So if you go to this link right here, it will, let me see if I can, if you go to that link, you'll come to this screen, or you'll hit a screen that says put your name in. You can just skip that and you should come to this screen. So then, if you're so willing, now you should see this. And basically, this is the first question. Should we emphasize fewer data types to enable more sampling locations? If you agree, like, yeah, that's a good strategy, cool, do it. If you're like, no, don't do that, bad idea, then if your answer is no to any of the questions we're going to ask, please, hit that button so it's like, no, don't do it, and write your own idea, your suggestion in the response box. So that's this box. You can put in your own answer, like you should do this other thing, and then hit submit and let us know. So this is going to be hard to get through these in the time. So if you could move quick. Okay, so yeah, if you agree, you just have to hit the thumbs up. You don't have to submit a response. It'll just track it. So, okay. I want to make sure people have time, but I also want to get through all the questions. So I'm going to give another like 10 seconds to hit whichever thumb you want to hit. And someone hit no. So if you said no, please, if you can type in a response or put it in the Google form or email us if you don't have time here. Okay. So I'm going to call that good. More response. NA. Interesting. Okay, so I'm going to call that good. I'm sorry if I'm cutting people off, but just to get through all of them, I'm going to deactivate this one. Apologies if you were about to hit the button or the thumb. These data types, surface water ions. Oh, sorry, I should activate it. Now you should see this next one, same setup, different question. The data types, surface water, ion chemistry, organic carbon concentration, and total nitrogen. So we get that along for kind of for free. We measure the carbon. And then sediment, bulk carbon nitrogen, ions, carbon, total nitrogen, FTICR grain size, microbiome. Oh yes, thanks. I'm guessing that's coming from Eric. Thank you. Microbial biomass, ATP, I think is the very specific analysis that is suggested. If people agree, you can hit that thumbs up on the microbial biomass. Or if you're like, you don't need microbial biomass, you can put that in as a response. It's all anonymous, by the way. The settings are all set to be anonymous. I can't see who's putting in what. Okay. Okay. Bulk N in the water, we're getting total nitrogen in the water. So when we do the NPOC, the instrument has both carbon and nitrogen, so we do get total nitrogen. I think I didn't say that before, so thank you for. Okay. Okay, all right. I think turbidity. We're not currently planning on measuring turbidity. To think about that. So this FTICR one, formula probability of metabolite and struggles. Yes, that's totally true. Interestingly, the last call we put up the suggestion of should we do LCMS as a complementary technique. There was very few positive responses to doing LCMS, which is why we said, okay, we're going to just focus on the FTICR. If people have strong opinions about that, please email us. That's probably the Google form. Sorry, the feedback form is really a great way as well. Okay, I'm going to hope that most responses are in. I'm going to deactivate this one in our last 30 seconds or so. Activate this one. So mostly collecting on a rolling basis, strive for this rapid ModEx, but also try to get at least 4 to 5 time points at 1 to 2 sites. If you have a specific thought, you can put in the response. As you know, I think you probably get the idea now of how this works. Please put in a suggestion if you think something else is needed. And I see your thought there in the chat, BK. Inorganic nitrogen changes in the respiration experiments. So those incubations run for like 2 hours. They're very short. Given that, maybe you can type in the chat, BK, is it worth doing the inorganic nitrogen kind of before and after if it's just like 2 hours for the incubation? Base flowstone period, yeah, thank you. Okay. 2 to 3 time points at 4 to 6 sites. Yep, trade-offs. Looks like some people like that as well. More time points at 1 to 2. Oh, interesting. Okay. Okay. All right. I'm gonna hope that most answers are in. Again, you got that Google feedback form. Please use that as well. And then probably yes, we are actually over time. I didn't activate. Sorry. So we equally weighted environmental extent and model uncertainty in terms of prioritizing sites. We can weight them in any way. It can be like 90% environmental extent and 10% model uncertainty. We did 50-50. Any parting thoughts on that? If you think like we should do something that's not equal, let us know. I'm just going to leave that one open because I know we got to go. say thank you again to you all. Super appreciate your thoughts. We will do our absolute best to incorporate your suggestions. And let's see, yes, and in particular, if you're interested in subsamples, that Google feedback form, I believe, has a question for that. Also, feel free to email us. Okay, so I'm gonna go. Thank you so much. Hope you all have a great rest of your day, evening, whatever it might be. And yeah, please reach out with any questions, suggestions, etc. Take care.